Welcome everybody to the April, we have an echo? Or is that just really loud? Okay, one moment. Okay, there we go. Turn the volume all the way down, that'll work. All right. Oh, technical issues aside, it's been a fun little small roller coaster getting here today. How many laptops did we try? I think 3. Maybe we almost tried a 4th one to get the presentation working, but here we are. Welcome. All right, so little safety slide today. Room hazards. We have cables behind the projector. Please be careful when you walk around there. Watch out for chairs with bags or umbrellas. Some of us are prepared for potential rain. Low lighting right now while we're doing the presentation. Any CPR certified attendees today? I'm not. I've done the training, but it was like a long time ago as well. Hopefully we won't need that. Emergency caller. Susan, thank you. Fire equipment. Okay, so we have a fire extinguisher in the back by that door. And remote attendees, please be aware of your surroundings. We have 2 exits in case of an emergency. One over there. And one through this door, and I believe down to the left. All right, real quick. We have a pile of upcoming events. We have Girl Scout Camp tomorrow. Then we have Martin Middle School Solar Science on the 14th. On the 16th, we have the Willard, downtown Raleigh. Stargazing with Sagan on the 25th, and Art Space on the 26th. 3 Bears for First Friday on May 2nd, and then May 15th, Weatherstone Elementary School in Cary. All right. On to the main event. You guys didn't come here to listen to me talk. So tonight we are joined by Dr. Treuthardt, Patrick Treuthardt. He works, his works deal with understanding the evolution of nearby galaxies and studying their different forms and structures. He's especially interested in barred and non-barred spiral galaxies and how their morphology connects to the supermassive black hole that they harbor in their nucleus, as well as the enormous halo of dark matter they reside in. Before joining the North Carolina Museum of Natural Sciences as the assistant head of Astronomy and Astrophysics Research Lab, he was a visiting researcher at the University of Alu, and a postdoctoral fellow at the University of Arkansas at Little Rock. Welcome, Dr. Treuthardt. And we're going to do our usual awkward switch of laptops now. So bear with us.
All right, thank you. Good. All right. Yes. All right. There we go. Okay. All right. Well, thanks for having me. My name is Patrick Treuthardt. I'm one of the 2 astronomers here at the museum. Like Naveen said, I study galaxies. I'm interested in spiral galaxies, their morphology and dynamics, so like the shapes and structures that make up these galaxies, and then the underlying physics that create these shapes and structures that we see. And for the past, I don't know, few years, I've been really interested in the connection between spiral galaxy structure and the mass of the supermassive black holes that lie in the nuclei of these galaxies. And so what I'm going to talk about, I'm going to introduce like all of this, but eventually what I'm going to talk about is a citizen science project that my collaborators and I are working on to basically efficiently kind of call thousands upon thousands of galaxies, trying to find a specific type of galaxy that we're looking for, basically using the help of the crowd, the wisdom of the crowd to try to figure this out. But all right, so we'll just get started. So obviously everybody's in the astronomy club, but who here has not seen the Milky Way? All right, so everybody's seen the Milky Way. Okay, excellent. So this is our own galaxy. This is essentially an all-sky view of the Milky Way, with the horizon taken out. And you can see on the bottom right, below the plane of the Milky Way, you can see the large and small Magellanic Clouds, which are satellite galaxies to our own. And if you notice, I mean, the screen projector isn't fantastic, but what you can see in the structure of the Milky Way, obviously, you see that most of the light is in a band, right? And then in that band, you have dark patches in there, and that's dust blocking out the starlight behind the dust. So the dust is absorbing it. But what you can also see is that if you look toward the center of the Milky Way is actually a different color than the outer parts of the Milky Way, right? So the center of the Milky Way is actually more yellowish orange, and the outer part's a little more blue. So the center region of the Milky Way, that's the bulge. So as you can see, it's slightly more puffed up. So you have essentially slightly older stars there, so it looks a little more yellowish orange, a little redder. But the outer parts of the Milky Way, you're looking at majority of the disk where all the star formation is happening, and so that's going to look bluer. So if you go out to a really dark area, if you guys haven't seen this, if you go out to a really dark area, you can actually see that color. And I grew up in Detroit. I mean, the only thing I ever saw was like Orion and the moon. And then it wasn't until I went to a conference in Hawaii and I ended up staying at the Big Island that it was so dark that I was actually able to see, first of all, the Milky Way for the first time in a long time. But that was the first time I actually saw the color of the Milky Way. Like you could actually see with your naked eye the color difference, which is just fantastic. I mean, especially if somebody who studies galaxies and knowing that this color, there's supposed to be a color difference, but to actually see it with your eyes is fantastic. It's really great. All right, so obviously the Milky Way is enormous, right? It's 100,000 light years across, maybe a little bit more. So there's no way to get outside the Milky Way to actually see it. So we have to get creative as to like how we determine what the Milky Way looks like. So it's like being stuck in your house and trying to map out the streets in your neighborhood, right? You have to be really creative about how you do it. So you have to like look through neighbors' windows to see the street behind their house, things like that. So you gotta be kind of imaginative, right? And so other astronomers have done this, and they've been able to kind of map out what the structure of the Milky Way looks like. And then this is a scientific illustration of from the data. This is what we think our Milky Way looks like. So it's a barred spiral galaxy. So you can see so down here in the center. Oh, I guess people in Zoom can see that. But right here, here's the sun, and right here's the center of the galaxy. And so you can see that yellowish orange bulge there in the center. But that bulge also, there's a linear structure running through that bulge, and that's the bar. And so most galaxies in the observable universe, or most spiral galaxies in the observable universe actually have this bar structure. So non-barred spiral galaxies are actually more rare, but I'll show you more about what those look like. But what's interesting about the Milky Way, specifically in this case, just a little tidbit, is that there is data to suggest that there are actually two bars overlapping and slightly offset from each other. And so that's what the illustration shows there, which is unusual because no other galaxy I've ever seen actually has that structure. So it could be the data, this could be conflicting data, and then maybe eventually one will shake out and the other one will be, like one bar may be true and one bar may not be, or it could actually exist, but somehow the dynamics hasn't settled down yet into a single bar. I don't know. It's an unusual phenomenon in that the Milky Way is the only one that seems to have that, as far as I know. Okay, so all right, so this is again an all-sky image of the Milky Way, but this is taken in the X-ray and gamma ray. And so you can see the plane of the Milky Way, but do you notice something else? Is there something else in this image that looks unusual compared to, for instance, that first image I showed you? See any like large scale structures that look a little different? No? Yeah. Yeah, right here. Yeah. Yeah, that's okay. Yeah, that's interesting. That's not what I was looking at though. That is a good point. Yeah. So it does look a little more puffy over here. But what I was actually noticing was, yeah, so you have the bulge right here, but then you have like a little diffuse region up here and then a little diffuse region down here, right? And so those structures are actually real. Those little diffuse regions perpendicular to the disk of the galaxy. And those are determined to be real, and those are now known as the Fermi bubbles. So this image was taken by the Fermi telescope, and these are remnants from basically energetic particles slamming into the intergalactic medium, which is just basically really, really diffuse gas outside of the galaxy. And so it basically heats it up and causes it to glow. So it's so energetic that it heats it up so much that it basically glows in the gamma rays. And so this is an artist's depiction of what we think this is actually showing here. So again, you got the Milky Way, the visible light Milky Way in the center there, and then the overlaid kind of artist's interpretation of the Fermi bubbles. And so these are actually, so in the previous image, they're not well defined, right? They're just kind of faint objects. So it's actually a light echo. So it's basically the remnants of these things. So they're basically fading out, like they're cooling down, fading out, no longer being visible in the gamma ray or in the X-ray. But this is what we think they look like in all their glory. And so the only thing that can be energetic enough to create these bubbles is what we think is a supermassive black hole. And so let's take a look at this. So this is another galaxy. This is not actually a spiral galaxy. This is just, I think it's a lenticular galaxy. I believe it's Centaurus A. But you can see kind of a dusty plane there in the center, kind of going up at about 45 degrees or so. And then you can see these jets of material shooting out perpendicular to the plane of dust, right? And then you can see kind of that little diffuse kind of bubble at the top, and especially on the bottom there, you can actually see what looks kind of like a jellyfish, right? And that's actually the shock front of that jet slamming into the intergalactic medium. And so it's basically it's shooting out, hitting the intergalactic medium and basically creating a shock front, like a bow shock in the front of it. So you can see kind of a remnant of a bubble on the top there too.
Get your images.
So this is I don't even know what telescope this was taken by. This is not taken by me. This is all pilfered from the internet. Yeah.
Yes.
It could be, or I tend to get a lot of stuff from ESO as well, so it could be European, from the Europeans as well. Okay, so again, this is an artist's interpretation. So if we zoom in the Milky Way, if we zoom in way into the nucleus of the galaxy, so let me backtrack there for a second. So when we look at that Fermi image, so you saw the plane of the Milky Way, but you didn't actually see those jets anymore. You just saw the light echoes of those bubbles, right? So we don't have those jets anymore. But that other galaxy, Centaurus A, still has those active jets. You can see that. So what probably happened was those jets were active in the Milky Way, and then something happened and they turned off, and now you're just left with the bubbles that are slowly fading out, right? So if we zoom in into the core of the Milky Way, we should see where the jets actually came from. So this is an artist's interpretation of how these jets actually form. And so if we zoom in way into the center, you can see the jets squirting out of this, out of the center of this dusty object right here. And so this is what's known as a dusty torus. So it's basically a donut. A torus is just a donut, right? And so what you're looking at is you're looking at the wall of the donut. So if you hold a donut in your hand, you're not looking through the hole, you're looking at the edge. Like you can't see the hole, you can't see inside of it, right? Because you're just looking through the donut. So if we zoom in, if we go inside the donut, this is what we should see. So if you look at the top left, you can see the Milky Way out there, and then it's all kind of blackish red, right? And so that's the wall of the torus, that's the wall of the donut. And now you're inside the hole of the donut. And what's happening in here is there's dust and gas falling onto a very large object, onto a very massive object. And as it's falling onto it, it's has an orbital path, and as it falls onto it, it basically orbits quicker and quicker and quicker as it falls onto that object, right? And so as it falls onto it, the stuff on the inner track is going to have a higher velocity than the stuff on the outer track. And when you do that, you actually have friction, right? You have viscosity. And what happens is that dust and gas heats up from that viscosity, and because it's moving so fast, it basically turns into a plasma, right? And so you have free-floating protons and electrons that are basically moving, right? And when you have a moving charge, you end up with a magnetic field. And so these charged particles can then get trapped in this magnetic field that's perpendicular to this disk here, this accretion disk that's basically of this plasma kind of falling onto this object. So you create this magnetic field that's kind of perpendicular to this disk, and these like electrons get trapped in this magnetic field and they get shot out at nearly the speed of light, well, not millions, but like thousands of light years outside the disk of the galaxy at nearly the speed of light. And so they have so much energy that once they hit the intergalactic medium, once they hit this gas and dust outside the galaxy, hits it with such force that it energizes it so much that it actually creates those bubbles that you see. So, and that's how we get these jets. And so the only way you can get this plasma, the only way you can heat up this gas and dust, create this plasma and create this magnetic field, is you have to have something that has a lot of gravity and a very small volume. You have basically a giant energy engine, right? And the only thing that can be is a supermassive black hole. So a supermassive black hole is a black hole with millions to billions of times the mass of the sun. Okay, and so this is really the only way you can get those bubbles that you see in other galaxies and that we see in the Milky Way. So this was really kind of the first hinting that we have a supermassive black hole in the center of our galaxy, is by seeing those Fermi bubbles, those light echoes. Okay, so we fast forward to, I don't know, like 5 years ago, and now we have technology has increased. We've got better telescopes, and now we have an image produced by something known as the Event Horizon Telescope, where they've actually photographed that accretion disk at the center of the galaxy. And so this is actually taken. So the background image is taken by EHT, the Event Horizon Telescope. The overlay is actually done by XKCD to kind of put it into scale. And so you can see the dot in the center is the sun's diameter, but that dark region in the center is actually the supermassive black hole. And that black hole is 4 million times the mass of the sun. Okay, and then you can see Mercury's orbit there. So basically the accretion disk is about the size of Mercury's orbit around the sun. So it's pretty big. But the thing is there's not enough material falling onto this black hole now to actually create those jets. So you need a lot of material falling onto it very, very quickly to basically be able to create those jets that have it sustained for a long period of time. Yep. Essentially it's a black hole image. Yeah. I mean, you can't technically photograph a black hole, but yeah, that void is where the black hole is. Yeah. So this is yeah, right. The sun's right on top of it for sure. Yeah. Yeah. So but yeah, so yeah, but this is about as close as we're going to get to a direct image of a black hole. So
I've heard this before,
yeah.
but I'm trying to figure out, how do you calculate theoretically the mass of the black hole that's in there? I don't remember how you do that.
Okay, well, so yeah, let's actually go to the next slide. So this is actually, in my opinion, probably the cooler way to see the black hole. But this is also probably the easiest way to measure the mass. And so what you're seeing here is a series of essentially photographs taken over decades of stars at the center of the galaxy orbiting around an unseen object, right? So this is actually prior to the Event Horizon Telescope, but after the Fermi bubble stuff. And so what you're seeing here is actually stars orbiting around the supermassive black hole. And so what you can do is by tracking the orbit of each one of these stars, if you know its period and you know its distance, you can use Kepler's laws to actually calculate the mass that they're orbiting around. And so each star gives you an independent mass estimate of the object it's orbiting around by using Kepler's laws.
Now they're in the mass of the stars.
Huh? Yeah, because the mass of the stars are the stars are essentially test particles compared to the black hole, right? Because the stars are going to be, let's say maybe 10 solar masses or something like that, right? The black hole is going to be 4 million times that, so it doesn't matter. Yeah, it's irrelevant. It's basically zero. Yeah, so each star's orbit gives you an independent mass measurement of the black hole. And and what's really fascinating about this, let's see if I could go back and do it again. Oops, yeah, okay. So what's really great about this, though, is you can see over the decades when they basically put in a new detector, because the resolution gets better, and that's real. It's basically the old detector in the beginning, and then they upgraded the technology, and now you got better resolution of the stars. So that's actually pretty fun too. Okay. So all right, so that's the Milky Way. So if we look at, I'm sure everybody's seen this, but if we basically, okay, if you go out into the night sky, right, or if you go out and you look at the full moon, right, the full moon, well, sometimes looks big, right, when it's along the horizon. It's actually only about half a degree in your field of view, and so this is just to give you a sense of scale here. But what Hubble has done in the past was they basically used Hubble to look at an apparent blank section of sky just to kind of see what was there, right? Just to kind of see how deep they could see, like they had no idea what was there. It's kind of like a mission of exploration, right? Just to see what was in this region that nobody's ever kind of explored before, just to see what was there. And so this region here, so you can see that little box with that the red arrow is pointing to. That's the scale size of something known as the Hubble Extreme Deep Field. And so that box that they looked at was about 1/20th of a degree. So the full moon takes up about half a degree in your field of view. The Hubble Extreme Deep Field was about 1/20th of a degree. Okay, so I don't know if most people kind of know this, but I mean, especially because you guys do telescope observing. But right, so a degree in your field of view, you can kind of approximate that, because if you stick your arm out, if you stretch your arm out, close one eye and look at your pinky takes up about will cover up 1 degree in your field of view, right? And so if you do this with a full moon, you can actually cover up the full moon with your pinky, right? Because the full moon is half a degree. So again, if this is 1 degree in your field of view, imagine dividing that up into 20 parts and then trying to look at that, right? So that's a very, very small section in your field of view that Hubble ended up looking at. So yeah, so there's the full moon. Okay, and so this is the Hubble Extreme Deep Field. So this is the region that they looked at, and this is what they saw. So they looked at a region where there were no stars. They didn't look in the direction of the Milky Way. They just looked at what they thought was apparently empty, opened the shutter and exposed for a long period of time, and then this is what they saw. So everything that you see here, except for, I think, this thing right here, and then maybe this right here, or that. So those 3 objects are probably stars in the Milky Way, but every other speck of light that you see in here is a galaxy of its own right, okay? And so they counted, there are about 5,500 galaxies in this small section of sky. So if we extrapolate this out to the entire sky, we now estimate there are about 2 trillion galaxies in the observable universe. Okay, so that's a lot of galaxies. And we also think that so far what we've seen is that every massive galaxy we look at seems to have a supermassive black hole in its nucleus. The thing is, we don't know how they get there. So we'll talk more about that. Okay, so again, so we have all these galaxies, and in the 1920s, 1930s, Edwin Hubble kind of noticed that there are all these extended objects, and when you end up with like a large sample of these objects, right, you start to automatically starting to look at correlations and trying to put things in, trying to bend things together, right? So like if if this is your first day on Earth and you go out into the forest, right, all of a sudden you see all these green things, you're like, okay, there's a lot of this stuff. I'm looking for commonalities now because I need to put things together to figure out what's what, right? So then you look at, maybe you'll see shrubs, maybe you see like deciduous trees, and then you see conifers and things like that, right? So you start to group things together. And so that's essentially what Hubble did as well. And so he noticed that there were basically two main types of galaxies. So there are elliptical galaxies, and these are essentially just giant balls of stars without real structure to them. So if you imagine holding one in your hand, they range from essentially like hoagie bun shaped to like a spherical ball. And if you kind of rotate it in your hand, you're not going to really see any difference, right? It's all going to look the same. And then you have spiral galaxies, which do have structure. Okay, these are very thin objects. So essentially, it's the spiral galaxies are basically very, very thin disks. So it's essentially like two DVDs stacked on top of each other is the ratio of diameter to thickness of a spiral galaxy. Okay, so they're very, very thin objects. So if you look at it edge on, it's gonna look like the Milky Way, right? But if you look at it face on, you're gonna see a ton of structure, right? So you're going to see galaxies that basically don't have a bar in the center, and then you're going to see some galaxies that do have a bar in the center, right? So barred spirals make up about 60 to 70% of spiral galaxies. So the non-barred ones are actually a little more rare. But what Hubble also noticed is that when you look at the spiral structure actually kind of correlates to the bulge size. So galaxies with a very large bulge tend to have the spiral arms more tightly wrapped, whereas those with a smaller bulge seem to have much more open arms. Okay. All right. So where do these galaxies come from? Okay, so this is an animation done by something known as the Illustris simulation. So this is just a high-powered computing simulation that was done more than 5 years ago, probably 10 years ago now. It's been a while. Yeah, it might be 10 years. And so what they did was they simulated a large volume of the universe from Big Bang to present, just using all the physics and math that we know of, right? And just basically crunched these numbers for a very, very long time and just kind of recreated kind of the formation and evolution of the universe on a large scale. And so what you're seeing on the left there is the dark matter in the large volume, and on the right you're seeing basically gas in that same volume. And so the right side is essentially where galaxy clusters are, so groups of galaxies that are bound together by gravity. But I don't know if you paid attention to it, but in the very beginning of this simulation, you didn't really see anything on the right side. You saw all the dark matter on the left, and the dark matter started to basically clump together and form these filaments, and then all of a sudden the gas started showing up in those filaments. So the dark matter is needed basically to gravitationally attract all the normal matter and basically funnel all the normal matter to where the dark matter kind of connects in these nodes, right? And that's where you end up with galaxy clusters. So again, there's more dark matter in the universe than there is normal matter, so that would make sense. So anyway, yeah, so what you're seeing here on the right side is essentially feedback from supernova explosions and basically the supermassive black holes in the centers of these galaxies, where you have just a ton of matter being dumped onto the black hole, and then it's basically shooting out all these particles and energy from that matter falling onto it. Okay, so that on a large scale, that's kind of how galaxies form. So you have this dark matter that basically gets gravitationally attracted together, forms these filaments, and then the normal matter kind of funnels down these filaments into these node regions, and then it forms galaxies and clusters of galaxies at these nodes. Okay, but how do the galaxies themselves in these nodes form? Okay, so honestly it's unclear, but our best idea is that there's something known as hierarchical merging that's happening early in the universe. And James Webb is kind of, the data we're getting from James Webb right now basically is kind of showing us that that's pretty much true. And what this is basically you start out with just very small clumps of matter. So if you look at this diagram, we're going from the top to the bottom. So you start out with these very small clumps of matter that are gravitationally attracted together, and then they'll merge together and form a larger clump. And then a smaller clump will be attracted to that larger clump, or large clumps attracted to larger clumps, so on and so on. And so basically you start building up larger and larger objects from these smaller objects, right? So it's a hierarchical emerging scenario, right? So at the end, so in present day, you'll end up with some very large galaxies, but you can also be left with some of the very small kind of dwarf galaxies as well. And so that's how we get kind of all the galaxies that we see now in the present day. Okay, so how do we specifically get spiral galaxies out of that? Well, if you have a large clump of matter, right, and you have these small clumps kind of passing by, the gravitational attraction between the large clump and the small clump, if it just kind of whizzes by, it can impart some spin to that larger clump. And when you have that spin, right, that clump is basically is mass, right, and it wants to gravitationally collapse. But if there's some spin to it, it's just going to collapse at the poles faster than it's going to collapse at the edges, right? And by doing that, then you end up with a very flat object that's spinning, right? And that's how you end up with a disk galaxy. So that's what you should see there on the right. Okay, so this is just a simulation kind of showing you what I just said. So here you have the hierarchical merging happening. So you see these tiny clumps kind of passing by, forming larger clumps. And then eventually what's going to happen is you're going to end up with a very large spiral galaxy. And so this is actually a really old simulation, but honestly, it's like one of the better ones I've seen. I mean, we won't play this forever, but I do want to, like, I want you to see the actual spiral galaxy form, because you can see, eventually what you'll see is, you see it becomes a very large disk. You can see all the spiral arms, but then eventually you'll also see a bar structure form too, which is great.
Mathematically created or artistically created?
No, this should be mathematically created. Yeah. Yeah, I mean, the nice thing about doing like galaxy simulations like this is that there aren't a ton of parameters, right? It's mostly gravity, velocity, like some stickiness to the particles, right? Like, you know, how if they're going to collide and stick together, or are they going to pass, you know, basically bounce off each other? You know, there's not a ton you have to really pay attention to do, you know, kind of basic simulations like this. Whereas like the Illustris, I mean, they're taking everything into account, right? They're doing a lot more stuff. But yeah, so here you can kind of see the disk already form. You see the spiral structure. You kind of see the bar, and it looks like it's spinning in the opposite direction, right? But I think that's just like that wheel effect, right? When you're driving next to a car that's, you know, it looks like the rims are spinning backwards, but they're really not. You know, they don't have spinners on it, right? They just have like the normal rims. So it's just that weird strobing effect. But yeah. Okay. All right, so that's how you form a spiral galaxy. So how do you maintain the arms in a spiral galaxy? Okay, so that's also not clear either. That's also a topic of research, but it's mostly accepted that there's something known as density waves that basically maintain the spiral structure in galaxies. Okay, so like the Milky Way galaxy has been around for, you know, billions of years. Right, and the spiral structure exists for a very, very long time. Right, it doesn't disappear. It doesn't wind up. It basically is maintained for a long period of time. So we see density waves basically all the time when you're driving on the freeway, right? So essentially, if you watch the nearby highway right here, what you're going to see is you see basically a clumping of cars, right? For honestly no reason, right? So basically you have particles moving in a path. And then there's a dense region where they all kind of slow down and group up, and then they just pass through that dense region and they keep going, right? So that dense region is the density wave. And what you see in the traffic here is the density wave is actually moving through the traffic backwards, right? So it's moving from like the exit out there all the way back toward the camera, whereas the particles are moving through in the opposite direction through the density wave. And essentially, that's what happens in galaxies as well, is you have a density wave structure that is passing through the galaxy, and particles are moving into and out of this density wave.
Did you go to the top of a cell phone tower to get that?
No, that was actually some like civil engineering website was displaying I don't actually know. Yeah, but yeah, it was from some civil engineering thing. I was fortunate enough to find that because it was perfect illustration. But yeah, so this is basically showing you how density waves can form spiral structure in a galaxy, right? So you start out with all these particles moving in circular orbits around the center of the galaxy. The particles in the center are moving faster than the particles in the outer parts. And then all you need is something to come by and kind of distort the orbits, right? So you just need to stretch out the orbits into ellipses and then offset the ellipses from each other. And now all of a sudden you end up with these regions where these particles are orbiting around still at the same speed, you know, same kind of essentially the same distance from each other on their individual orbital paths, but they end up in regions that clump together, right? So if you imagine all these points being gas clouds, like very large gas clouds, they're going to be, you know, they're going to be regions where they're spread out far away from each other, but then they're going to encounter these regions where they're going to be a lot of gas clouds all kind of bunched up. And when you have that, these gas clouds smash into each other, condense, collapse, and form stars. And these stars light up those dense regions and then show you where they are. And then these are the spiral arms that you see, right? So this is just an illustration here of what I was talking about. If we look at a specific arm, right? So you see a gas cloud on the top there, and as it passes into the dense region, it condenses and collapses, and then it forms like all different mass stars, right? So you end up with low mass stars that are kind of yellowish and red, and then you end up with high mass stars that are very blue. The high mass stars, the blue stars, are going to be much brighter, are going to burn much hotter than the small mass stars. So they're going to overwhelm the light of the low mass stars. So that's going to basically make the arms look blue. So just like when we talked about in the very beginning with the Milky Way picture, if you look out into the edge of the disk, it's going to look bluer than the center, right? And that's because that's where all the star formation is happening. And then as the stars pass through the rest of the spiral arm, the blue stars, because they're so massive, they'll burn out very, very quickly. And then you're just left with the red stars, the small dim red stars that just kind of move out of the arm. And then they spread out from each other and they become so dim that you don't really see them anymore. And then until they basically go supernova, turn into a gas cloud, right? Then you have a gas cloud that goes into another arm, and then the whole thing starts over again, right? So it just keeps going on and on like that. And so that's how you can maintain spiral structure in a galaxy. Yeah.
Just back on this.
Yeah.
I'm really curious about how it is that we actually have the flow of matter into these spiral arms.
Yeah.
You look at Orion Nebula, something's got to be feeding Orion Nebula. So is the gas in the galaxy that's actually flowing into the spiral arm, that's becoming compressed.
Yep.
And that's what's being illuminated by the stars that are around it that are forming.
No, the gas clouds themselves, when they enter. So if you go back. Sorry, I wanted to show you the video again. Sorry, I have to go probably past this one. Hold on. Okay. Yeah. So if these are all gas clouds, right? So what's going to happen is those gas clouds. So right now they're not touching each other. They're not going to hit each other. So they're just going to be gas clouds, right? And so eventually what's going to happen is all this gets shifted, and then you end up with the spiral structure. So now these gas clouds are basically on intersecting orbits, right? And so when you have that, then they're going to collide with each other. And when they collide, they're going to compress. Yeah, and that's where you get the stars, right? So now it looks like a jumbled mess right here, right? So here's more chaotic. And this is where you get all the star formation then from that gas. And I mean, it takes the stars a long time to pass through there, or the gas clouds to pass through that. So right when it hits the front edge, right, they'll collide, form new stars, and then those stars have to continue that orbital path. But it takes them a long time to get through that dense region, right? And so basically, it's mostly going to be blue stars in the dense region because they're going to burn out quickly, like hundreds of millions of years. Well, sorry, millions of years. And then basically they continue on their way, right? So those blue giants are basically going to go supernova and then distribute gas back out into clouds, and then just kind of recycle it again and again. Yeah. Okay. Yeah, it's pretty cool, right?
It's in certain places you'll see like in an eddy or whatever. Where you actually get a wave that appears to pop up.
Yeah.
It doesn't go anywhere.
Oh yeah, like a standing wave. Yep.
Right.
Yeah.
So you got fluid flowing through that wave. And
Yeah.
the wave stays there.
Yeah.
So anything that gets caught in that,
Yeah.
it's really hard for it to get out.
Right. Yeah. Yeah, I mean, yeah. I mean, in a way, yeah. I mean, in a way, it is a standing wave, right? But not quite the same, but yeah. But it is similar, right? Because I mean, because the interesting thing too, I mean, from what I study, is that there's a material speed in the galaxy, but then there's also that pattern, right? That spiral pattern, and that has a speed as well. And so, I mean, if we talk about the Milky Way, right? Like one of the interesting things that people have thought about is, when they're searching for life, on different planets and stuff, they think about, okay, there's like a habitable zone for planets, right? Like you want to be a certain distance away from a star, so a liquid water can exist on the surface of a planet, right? That's where you want to be. People have also thought, well, is there a habitable zone for a galaxy, right? For like the Milky Way, the preferred zone where you want to be. And one of the things people have thought about is that, well, if the material speed is the same as, or is very similar to the pattern speed, so if the spiral structure is moving at some speed and the material speed is about the same speed, then you spend very little time like in the actual spiral structure, right, where all the supernovas happen and stuff. So you spend very little time in that structure, like let's say the planet forms, right? It moves out of there, or the star forms with the planets, it moves out of there. And now it takes a very long time before that star enters another spiral arm where supernovas could happen again, right? Maybe wipe out the atmosphere of a planet. So it's thought that that co-rotation radius, that radius where both the pattern speed and the material speed is the same, may actually be important. And the sun seems to be at near the co-rotation radius of the Milky Way. And so, is that coincidence or is that important? I mean, nobody knows, right? But it is interesting to think about. Okay. Okay, so we talked about galaxies. So this is a timeline of the universe, right? So the universe is about 14 billion years old. And so here on the left, we have the Big Bang here on the very left there with the quantum fluctuations. On the right, we have where we are today. But here we have the first stars, right? The first stars form about 400 million years after the Big Bang, which is very, very quick. This is also where we start to see the first galaxies, when we start to see those proto-galaxies, right, from the hierarchical merging. We also see supermassive black holes at that same time. So the problem is the theorists have a hard time trying to create supermassive black holes in the centers of galaxies that are millions to billions of times the mass of the sun in that short amount of time. So it's hard to understand how that can basically form and evolve so quickly. And the problem, and more of a problem now, is that James Webb is seeing some of this stuff a little bit earlier than that. So the theorists are now having a harder time to account for that. So it's becoming a little tougher for these guys. Okay, so the problem is like, where do these supermassive black holes come from? We don't know. So what we do know is that there are something known as stellar mass black holes, right? That range from, I don't know, like tens to 100 times the mass of the sun. And we know where these come from. These are basically giant, these come from like blue giant stars that collapse at the end of their lives. And there's so much mass that the core just collapses into a black hole, right? And the core that's left over is basically these stellar mass black holes. And we see these supermassive black holes that range from millions to billions of times the mass of the sun. We don't know where they come from, but we know they form very quickly or very early in the universe, basically along with galaxies, but we don't know the mechanism. What we don't see is anything between those. We don't see what's known as intermediate mass black holes that range from 1,000 to 100,000 times the mass of the sun. So we don't see that. But we think that maybe intermediate mass black holes may be the key to understanding supermassive black holes. Okay. So again, where do supermassive black holes come from? They could come from, for instance, like the direct collapse of giant gas clouds. So these, very early in the universe, you could have these giant gas clouds that are so massive that they just collapse under their own gravity, and they collapse with so much mass that it collapses directly into a supermassive black hole, or at least seeds, right, into these intermediate mass black hole seeds that then merge quickly together and form a supermassive black hole. Yeah, I'll get to that. But yeah, so they could be directly from large gas clouds. They could be the remnants of the first stars. So you could have like these, what's literally known as population 3 stars. These are like the very first stars that formed in the universe that are purely hydrogen and helium. because no other elements really existed yet. And so those could get very massive and burn very quickly and could collapse into these intermediate mass black holes. Or maybe you just have these stellar mass black holes, just a lot of them that form quickly, that merge together very quickly, form intermediate, and then these intermediate merge together very quickly and form a supermassive black hole. It could be anything. It could be any one of those things. So the key is intermediate mass black holes. But the problem is we don't see them. So does that mean that they either do not exist, that they so rapidly grow into supermassive black holes that we just don't see any in the nearby universe? Or is it that they're just not easily observed? That they do exist in the nearby universe, but we just have a hard time seeing them. And I'm betting on that we just can't find them. If it's the other two, I mean, we won't know. But if it's the last one, if they're just not easy to find, then that's all. Then maybe we just need to look harder to try to find. Yeah.
So
they've found candidates, but not in the centers of galaxies. So they found an intermediate. I think they found intermediate mass black holes, like in globular clusters. So these star clusters in galaxies. I think they found some, like maybe they found. I mean, again, it's not many. It's maybe like a dozen, or 6, or something like that. I think they found some in the outer parts of a galaxy. I think maybe there's a candidate for one in the center of a galaxy. I'm not sure. But we have not found essentially 0. We found essentially 0.
Supermassive black hole.
Mhm.
Each galaxy, well, most galaxies
Yeah.
have that super.
Yeah.
massive black hole,
Essentially every galaxy we look at. Yeah.
except maybe this one.
Yeah, that's not clear. Yeah, I don't know. Yeah. Yeah. Yeah.
So we haven't found an intermediate mass black hole in the center of the galaxy.
Right.
Okay.
Yeah. Yeah. And so if we can find, so the idea is, okay, sorry. So the idea is if we find, let's say we find a galaxy, let's say we find a dozen galaxies that have intermediate mass black holes in their centers, right? These galaxies are going to be outliers compared to every other galaxy we look at, right? So there's going to be something different about these galaxies than every other galaxy we look at. And so if we can get like a dozen of these galaxies, right, that have intermediate mass black holes in the centers, if we can determine what stopped the evolution of these black holes into supermassive black holes, that will actually tell us something about how black holes and galaxies evolve in general, right? If we can find out what makes these different from every other galaxy, that will tell us something about how galaxies evolve. And so the goal that I'm trying to do, the goal of my projects is trying to figure out how we can find candidates that are intermediate mass black hole galaxies, right? Instead of looking at every single galaxy, doing spectroscopy on the center of every single galaxy, which takes like a night per galaxy, right? Nobody's going to give you time to do that. But instead of doing that, is there a way that we can do it very easily and like cull thousands upon thousands of galaxies, find 2 or 3 that then we can follow up with telescope observations to confirm whether or not, yes, this is an intermediate or not, right? And then we can start pulling out those galaxies, putting them together in a bin, and looking at the commonality between those. Okay, so how can we do that? So one thing that's interesting is that there's a relationship between the mass of the supermassive black hole in the center of a galaxy and how tightly wrapped the spiral arms are in a galaxy. Okay, so if the arms are very tightly wrapped, the mass of the supermassive black hole in the center is very high. If the arms are very open or loosely wound, then the mass of the supermassive black hole is actually very low. Okay, so this winding here is a term we call pitch angle. So if the pitch angle is low, then the arms are tightly wrapped, the black hole mass seems to be high. If the pitch angle is high, the black hole mass seems to be low. Okay, and so if we use this relationship, so right here, this is a million solar masses right here. But if this relationship holds for lower mass galaxies, right? We don't have any galaxies at that lower end. But if the relationship holds for lower mass galaxies, we just have to find galaxies with pitch angles, let's say above 25 degrees, right? So maybe a 30-degree pitch angle galaxy, we just have to find those. And then those potentially harbor intermediate mass black holes, right? So we gather up all those that we can find and then measure the basically the scattering of the stars in the center to determine the black hole mass in the center and see if they really are intermediate mass. And then we have our sample, right? So that's the idea. Okay, so the best way to do that is to use all sky surveys, right? Instead of taking your own telescope, going out and looking at every single galaxy, right? That's already been done, right? Their giant telescopes have taken pictures of sections of sky that happen to have stars and galaxies in them, moved the telescope over, taken another picture of the sky, right, with galaxies and stars in them. So what we do is we just pull out all the galaxies that they've seen and try to measure those, right? The problem is that these telescopes were not, they weren't purposely looking at galaxies, right? So you end up with images that look like this, right? This is a spiral galaxy that's essentially face on, right? So this actually has spiral structure in it. I don't even know if, I mean, the projector resolution isn't fantastic, so it's harder to see here than it is on the screen, but even on the screen, it's pretty bad. Yeah, right. But yeah, so there's like spiral structure kind of right here, something like that, and then like right here. But yeah, so the problem is, so like in this image, the contrast between the arms and the interarm regions, right, the brightness level is essentially the same, right? And so a computer is going to have a really hard time distinguishing where the arms are and the interarm regions, right? And so, but the thing is like people are really good at seeing patterns, sometimes patterns that don't exist, but they're really good at visually seeing patterns. And so we thought we'd take advantage of that and have people actually point out to us where the spiral structure is in these 4 contrast images, and then we can measure what people identify for us, okay? And so this is just kind of an idea of what we do, right? So we show people a picture of a galaxy, we have people trace out the arms of the galaxy that they see, and we throw away the image of the galaxy, and then we just measure the tracings that people give us, right? And that's an easy way to basically identify the spiral structure and an easy way to measure it, right? And we have software that can measure the spiral structure. So what we did was we built a citizen science project called Spiral Graph, which essentially showed people images of galaxies, and we had them basically trace out the spiral arms. And so what we had to do, because every galaxy is not face on, right? We wanted to give every galaxy kind of equal footing for people, so they all kind of look the same. So you end up with some galaxies that are kind of edge on and some galaxies that are face on, but we want to make them all look like they're face on. So the first thing we had to do was take the image, and we had to what's known as deproject it, right? So we deprojected it to face on. So what you do, the simple way to do that is you fit an ellipse to the outer edges of the galaxy, and if the galaxy is face on, that ellipse should actually be a circle, right? And so all we had to do is basically stretch the image so that way it became a circle, and then you basically get a face-on galaxy, right? So we fit an ellipse to the outer parts, we rotate the image, and then we stretch along the short axis until it's a circle. And now you end up with what looks like a face-on spiral galaxy. And so we do that with all our images, so that way all the galaxies look face-on, and then we have people trace out the image. So the galaxies that we used, so we had to pull out all the spiral galaxies because they're ellipticals as well, right? And so in order to find out where all the spirals were, we ended up using data from another citizen science project called Galaxy Zoo, which some of you may have heard of. And that's basically, that project is basically they show people pictures of galaxies and they have you identify it as spiral or elliptical, right? And so they published their data. We took all the spirals, all the ones that were identified as spirals, and then we downloaded the galaxy images and then used it in our project. The problem is that Galaxy Zoo, we found out, is not accurate, not 100% accurate. So we had to kind of reclassify these galaxies as spiral or something else, because they're not all spiral. So for instance, this was one of the galaxies that was identified as a spiral, and that's one of the galaxies identified as a spiral. This is not a spiral. This is basically 2 galaxies merging, and that clearly is a spiral. So the first thing we had to do is basically show people a picture of the galaxy and say, is this a spiral or is this something else? And so if it's something else, we say, okay, thank you, and then we throw this, we put this image away, and then we show them another image until they get to a spiral galaxy, and they say, yes, this is spiral, and And we say, okay, now trace out the arms that you see. And that's part B over there. And that's basically how the entire project worked. So we ran this during the COVID pandemic, essentially right when it started. And we plugged in about 6,222 galaxies. And surprisingly, we were done in about a month. We had 15 people look at each galaxy, identify it and trace it, if it was traceable. Yeah, and we've got done in a month. So then we basically harvested 14,000 more galaxies and plugged that in. And then we were done within a year with those. And then we just stopped the project because we have too much data. So we didn't want to keep running it because we wanted to actually process some data before we start wasting people's time. So we just paused it, and now it's paused. So this is the reclassification data that we have. So out of the essentially 6,000 galaxies, 2,300 galaxies were identified as clearly spiral galaxies by everybody, by most people. So by 68% of people or greater said that about 2,500 galaxies were clearly spirals. But interestingly, between 0 and 32% said about 900 of these galaxies were not spiral galaxies. And exactly 51 galaxies, 0 people thought were a spiral galaxy, although Galaxy Zoo said that they were. So there's some error in Galaxy Zoo. But yeah, so we ranked the galaxies that we have. We have classified those. All right, and so this is an example of tracings made by 15 different people of a galaxy. And here you can see the spiral structure now. It looks much better. I mean, it's not the same galaxy as I showed you before, but clearly you can see spiral structure now, right? And so now we can just plug this into our software, and then we can basically measure the pitch angles, and then we can figure out, what the black hole mass is, or estimate the black hole mass. Yeah, so people are not 100%. Yeah, I mean, there's some that are just wacky too, right? That is an outlier, yeah. Yeah. Yeah, so this is, okay, so let me just point out what's going on here. So the bottom part of this plot are the pitch angles that we determined for these galaxies. And then these are the pitch angles determined by an independent method by a different group for the same galaxies. Okay, so ideally, all these data points should lie on this black line. But instead, what you have is basically a cloud of points where everything is kind of around the black line, right? Ideally, they should all lie on exactly the same line. Like, we should be measuring the same thing. We're not. And the problem is that there's no right answer, right? There's no right answer to what the pitch angle is for a galaxy, right? Like, they measured it one way, got this answer. We measured it another way, we got this answer. Who's right, right? So basically, we want to be less wrong. So we want to double check our numbers to make sure that we're not doing it wrong. Like maybe there's a different way to do it. Maybe we can come up with better answers that maybe match theirs. So what we're doing now is we're kind of rechecking our answers.
So that's how you would get rid of the errors, or is there an error percentage that you're?
You mean for actual measurements?
Yeah, I mean, some of those are really outliers.
Yeah, yeah.
So how would you measure? Like, how would you deal with?
Yeah. Well. Yeah. Well, I don't want to throw away data because you don't know if it's valid or not, right? The other problem is that this group, if you look, you can see all the error bars are horizontal. I don't know if you can see that. That group has no error bars in the vertical. They reported 0 error on their measurements, which I do not agree with. And they make no excuse as to why they measured 0 error. There should be some error. They just did not report it. I don't know how it got by the referee, to be honest. There should be an error measurement with that. So we have to assume, because they reported no errors, we have to assume that their measurements are 100% accurate, which I do not agree with. But we do have our error bars, right? And you can see, obviously, the outliers way out here have very large error bars, right? So like, I mean, there's a galaxy here that's like 80 degrees. There's no way that's real, right? But the error bar goes all the way out to like 60, which I still don't believe either. That's way too high. So, I mean, yeah, that's probably wrong. That's probably like some that we have to visually look at, look at the image and be like, okay, what's going on here? Is this right? And it could be it's like a merging galaxy. It could be one, I mean, there's some galaxies that, are basically like tidal tails, right? So they're very linear structures instead of really wound, right? And that's clearly a merger. That's not like kind of self-evolving spiral structure, right? That's clearly from something external. That doesn't really represent the internal dynamics of the galaxy with the black hole, right? It's something external that affected it. It could be that, right? So it's, yeah, we'd have to go through and look at some of these outliers and see what we can determine. You could do that, yeah, but I mean, eventually we're planning on doing this for like millions of galaxies. And so we want to bypass as much of the manual stuff as we can, right? Yeah.
Basically, they're trying to map the entire sky 4 times within the next 5 years or something like that.
Oh, you mean the Vera Rubin telescope?
Yes.
Yeah. Yeah, well, when that comes online, for sure. Yeah. Yeah. Right. Oh, really? Yeah. Yeah.
It is interesting that they're going to be mapping it in looks like 6 wavelengths.
Yeah.
6
Yeah. Yeah. Well, yeah. I mean, but you also don't want, I mean, there's a limit too, right? I mean, you don't want like poor contrast and really poor resolution, but you also get hindered potentially by really high resolution, right? So if you're looking at high, if you're using like Hubble images, there's a problem with that too, because you're cutting out like the outer parts of the galaxy in some cases. Like if they're really nearby galaxies, the field of view for the Hubble is pretty small. So you kind of need like a smaller telescope. But like the Vera Rubin, I mean, I don't actually know what data is going to become available because it's supposed to be looking at transients, right? It's basically taking images of the sky and then taking images of the sky again and then subtracting it out, and you're left with like the supernovas and all the variable stuff and like the constant things they kind of get rid of. At least that's my understanding. I don't know what they do with that data because it's going to be like terabytes per night, right? So I thought they're deleting a lot of it. So yeah, so I don't know. Yeah, I mean it's definitely on the radar, but the problem then too is those galaxies aren't classified as spiral or elliptical, right? So then we have to go through like basically galaxy zoo. Yeah, we have to do galaxy zoo on those galaxies, pull out the spirals, then run spiralgraph. And then, I mean, we'll get to the next thing, but we'll also have to do the next thing too. So yeah, but I mean, it's a potential. Yeah, we could potentially do it, but I don't think we quite need to do it yet. We still want to perfect what we're doing now, and then if we think it works, then yeah, then we want to like scale it up with lots of data, like millions of galaxies. Yeah. Yeah.
So you have a correlated data that does fall on the line that you're able to use?
Well, I would say no. I mean, so okay, so the reason why the points are different colors too is because the green. So again, with the bar graph, right? We had the green ones where most people agree they're spiral galaxies, and then we had the red ones where, well, sorry, we had the red one. We eliminated the red ones completely, right? But we had like high agreement, medium agreement, low agreement, and then basically nobody agreed. We just didn't use those galaxies. So the green is where most people agreed, the 68%. So that's all the green points. And then the green dashed line is the fit. And so it should be a slope of 1 with a y-intercept of 0. And then that rho h should actually be 1, but it's 0.44. But now if we take the high and the medium, so the green and the blue, that's the blue dashed line. Slope is 1, y-intercept is closer to 0 than before, but now the correlation coefficient is lower than just taking the high ones. So now if we do the high, medium, and low, that's the pink or the magenta, right? Again, the slope is better, the y-intercept is better, but the correlation coefficient is worse. Yeah, well, no, we haven't. I mean, because there are a lot, but then also, the problem too is that, honestly, the problem is that I don't agree with these people's numbers. They have no errors, and then, I don't want to go off on these people, but I don't buy it. I don't buy it. The only thing we can do is improve our own methods, and we improve it to a point where we can like robustly defend it and say, look, this is the best we're going to do with this. We think this is right. If these other people think they're right, then they can like defend their own method and say how it's better, right? Yeah. Right. Exactly. Yeah.
Validation.
Hmm.
And have people error.
Yeah.
So
Yeah. 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 Well, hopefully that's not the case. Yeah.
hopefully modules.
Mm-hmm.
I hate to say no.
Mm-hmm.
Just again, culturally,
Mm-hmm.
sometimes adverse to reporting error. Like that.
Yeah. 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 Well, I do know who did it. I mean, they're from California, so I don't know. Yeah. I will leave it at that. Yeah. Okay. So, all right. So, okay. So one way that we're trying to improve our process. So instead of taking all the tracings, right, of the entire galaxy and plugging it into our software and measuring basically all the arms at the same time, and coming up with the pitch angle of the galaxy all at once, we thought, okay, maybe what we need to do is actually measure each arm individually, and then combine those measurements into a global pitch angle value for the galaxy. And then how we combine that may be more accurate or not, right? So like if we go back here for a second. So if we look at this image here, right? All these arms are not the same, right? Maybe like if you look at the shorter arm here on the inside, right? It doesn't have really the same winding as this other inside, right? So it actually has two different pitch angles in this galaxy already, right? So maybe we have to add more weight to the longer arms than the shorter arms, or vice versa, or maybe we just average them all together and then figure that out. So the software that we're using basically assumes that the image is completely symmetric and tries to fit it as best it can with the model, and then it measures the model, right? And the model may not be 100% accurate then. But if we measure each arm individually, the model should fit that model arm very, very well, and then we can get that measurement for that individual arm and then combine that somehow, like weighted average, straight average, whatever, things like that, right? Luminosity weighted thing, whatever. So the idea is okay, so now we have that nest, like that bird's nest of tracings, right? So how do we pull out individual arm structures from that bird's nest? And that surprisingly is a very difficult project. We tried for about a year using all different types of AI methods, all different types of AI tools to pull that out, and nothing worked. Because the problem is you can get zones of data, right? But when you have spiral structure and kind of overlapping spiral structure, AI cannot distinguish that overlapping spiral structure. It cannot distinguish it. So so a grad student came up with an idea. Well, we both came up with this idea, but he developed the actual technique. Where, okay, what if we just take a tracing, just take a single tracing, and we compare it to all the other tracings that people have made for the galaxy. Okay, and then we start bundling things together. Okay, so we take a tracing, we basically blur it so it becomes fatter. And then we take another tracing and we subtract it from the original, from that blurred tracing. And so if a certain percentage of that second tracing fits within the blurred image, then we say, okay, these two belong together. And then we bundle those together, we put those into a folder, right? And then we take another tracing, we do it again. And we keep doing it, and we keep doing it, and we keep doing it. Eventually you end up with, you know, a folder full of tracings that all combine together and a folder full of tracings that don't combine together. And then you go through that folder where they don't combine together, and then you start combining those together until you get bundles of tracings in different folders, and then you have all the arms separated. Okay, and this is basically showing you the process, and here you have a set of tracings that are all bundled together that form an individual arm, right? And so this is the result for that galaxy with the outlier. So the nice thing is that the grad student, his method also eliminates outliers, right? So that outlier is no longer in the equation anymore. So these are the original tracings. These are the group tracings, the clustered tracings, broken up into different colors for the different arms, and then this is just the overlay of the two, right? And so you can see that the faint arm here is no longer in a group, and you can see some of these other ones here are no longer clustered together either. But now we have the individual arms, so we can measure the individual arms and then combine them together. Okay, so we found that this works about 80% of the time on the high confidence spirals, which is not fantastic. It sounds good, but it's not fantastic. With the high confidence spirals, like all those the ones in the green bar, right? We want to get those like way higher, because we're going to run into like the medium and low galaxies, right? Where it's going to be much harder to get a lot of tracings and cluster those together. So the problem is with the high confidence spirals, like the clustering doesn't always work. So for instance here, obviously this is a 2-arm spiral, but it was only able to cluster one of the arms for some reason. It didn't get the other one. And then here, again, it's a 2-arm spiral, but it saw them both as a single arm, right? And so basically all we have to do behind the scenes is kind of tweak the hyperparameters a little bit, and then it'll fit. But that's a lot of manual labor for, you know, I mean, it's 80% of 2,000 galaxies worked, and then 20% didn't, right? So that's like 400 galaxies, 400 galaxies, right? We want to do that by hand. We want to do that automatically. And so we came up with the idea to build another citizen science project where we essentially cluster all these tracings, show people images of the clusters, and then have them tell us, did it work or did it not work? Like swipe left, swipe right, right? And behind the scenes, what's happening is we know all the hyperparameters that went into making that cluster image, and then we're basically just generating data for an AI to determine the correct hyperparameters for a given type of galaxy image, right? A given type of tracing image. And so eventually what will happen is we'll develop basically a training model from all these people telling us what worked and what didn't, and then we basically show the AI the tracing image. It says these are the hyperparameters that will probably work. You plug it in, get the clustering image, and then we're done. We move on to the next image. So that's the idea. So this one is called, so it's a daughter product of Spiral Graph, so we're calling it Spiral Graph Cluster Buster. And so if you're interested, you can go to this URL. We're still building it, but it is now actually officially sponsored or funded by NASA for a year. So we should hopefully get money on May 1st for this. But yeah, so NASA thought it was good enough to give us some money to try to work on this. So starting May 1st, we're going to really start working on building this and getting it running. Skeleton is up if you guys want to try it. There's nothing in the about. There's nothing in the talk. That all still needs to be built, but the project should work right now. No, that's again, this is temporary. That's AI generated garbage that I put on there. Yeah. Yeah. I'm like, I told, I think it was Gemini, I'm like, give me an image of strings, spiral strings or something like that. And so it created that for me. Yeah. But yeah, so basically that's it. So yeah, so it's just summary. So yeah, so essentially we're trying to find intermediate mass black holes by culling, lots and lots of images, by having people trace out spiral structure, looking at the pitch angles of galaxies to determine black hole mass. If we can find some very high pitch angle galaxies, those might harbor intermediate mass black holes. We collect all those, we apply for telescope time, hopefully confirm that they're actually intermediate mass black holes, and that's when the fun begins. That's when we start to try to figure out where why these galaxies stopped forming supermassive black holes. Was it the environment? Was it something internal? Why didn't they become supermassive black holes? And then that'll tell us something about how, for instance, the Milky Way got its supermassive black hole. Why the evolution continued in our galaxy, but not in these galaxies. And that's it. And then the little animation on the bottom is just kind of showing you the entire process from image through spiral graph through cluster buster. So, yeah.
I'm gonna phrase this question,
Yeah.
but I'll try, I guess. So you look back in history and you think, well, at one point we, use Newtonian physics to kind of measure things, and then we find out that they'd be traveling really, really fast, and there's some other rules of physics.
Yeah.
Deal with those, small things. You get really weird stuff happening in quantum world and quantum entanglement and things that just don't make any sense. Wouldn't it be reasonable to assume that when you're talking about the nature of big galaxies and all the simulations of the hierarchy merging, that there might be physics out there that we just will never ever understand?
Well,
We can't explain it with what we know from what we learned on the Earth and in the solar system.
maybe. I mean, maybe. I mean, yeah, but I mean, but it's going to pop out, right? I mean, like the thing is, like relativistic stuff. I mean, that pops out because, I mean, relativity, part of relativity that was, part of the hints to relativity was like the weird orbit of Mercury, right? So there was like a precession of Mercury that couldn't really be accounted for, other than like the gravitational field of the sun, right? So which is like a relativistic effect, right? And then once once Einstein's relativity came about and things like that, like it accounted for it like perfectly, right? Now we can predict the orbit correctly, right? I mean, like in my case with this stuff, it's not really weird stuff, it's like we're not working at really weird scales. I mean, the only kind of weird thing that could happen is maybe there's some kind of like dark matter effect, but I mean, it could be, because these halos of dark matter, they're probably not perfectly spherical. They could be like oblong, like an ellipsoid, and maybe that's spinning. And when that happens, maybe that can change, because all the galaxies are sitting in this dark matter, right? And so maybe that's imparting some spin or some dynamics on the external structure. But again, is that really going to matter? I don't know. I don't know.
Dream about coils and helixes and stuff.
No, but I do have. Yeah, I do have a lot of spiral t-shirts for sure. Yeah.
Patrick, we have 3 questions on Zoom.
Okay.
First one, regarding the Event Horizon Telescope's image of Sagittarius A star. What is this? Do you know what the angular field of view of that was?
Oh, no.
Okay.
No, sorry.
All right, next.
But you can backtrack it. Because so you can look up, well, I guess you could look it all up, right? But you could look up the distance. Well, so the distance to the center of the galaxy is like 8.5 kiloparsecs. and the size is essentially the orbit of Mercury. So S equals d theta. So S is the true size, d is the distance, theta is the angular size. So you can figure it out, but yeah. Yeah,
Person asking
or
the question will do that.
yeah.
Okay, next question. What are the prevailing theories as to why James Webb Space Telescope is seeing these massive objects so soon after the Big Bang?
Prevailing theory. I don't know. I think the thing is I think everybody's kind of surprised that we're seeing it that early. I mean, the problem is like the theorists have to keep up with that now, right? Because it's a balance between observation and theory all the time, right? So people can come up with these theories, and now all of a sudden there's an observation that refutes that, and it's like, oh, now we got to recreate these theories, right? We need to tweak the theory so that way it fits what we actually observe, right? And it works until it doesn't anymore. Until you see something else, right? You're like, oh, wait, this isn't the same anymore. What's happening here? You know, so now the theorists have to go and try to explain that, right? So it's always kind of a balancing act. And I think we're in the phase now where James Webb is seeing stuff that the theorists haven't accounted for. So now the theorists have to kind of go back and figure it out. And I don't know what the status of any of that is, to be honest. Yeah.
Third question. Have globular clusters been ruled out as a possible home for some of these objects? I assume the intermediate mass
Yeah.
holes.
No. I think most of the candidates are in globular clusters. But yeah, but that's not helpful for me. Yeah.
Okay, I'm sorry. And there was a fourth one, unrelated to the topic.
Yeah.
But what are your thoughts on how globular clusters formed?
Yeah. So, well, I mean, this goes back to like my introductory astronomy, which is, decades ago. So I don't know if things have changed because I don't really study these things, but it's my understanding that, when the disk of the galaxy formed, it kind of collapsed. But then there were these dense regions that collapsed on their own and didn't fall, or they have like random motions through the galaxy. And so they're basically, I think they condensed out of the gas and dust cloud as it collapsed into the disk. I can't remember if that's exactly true or not. That's my impression. It's been a while. It's been a long time.
Oh, it was asking for your thoughts on it.
Okay,
So
well,
there you go.
we'll give you that.
Right.
We'll call that my opinion.
No more on Zoom.
Okay.
Anybody else in the room? Questions?
So, so you're not looking at any galaxies that have had interactions, right? So there's some galaxies that look like they just kind of lost their ability to hold their spiral structure
Right.
altogether.
Yeah.
So they must have interacted with something that caused that.
Right.
So you're not looking at any of that, right?
No.
That don't appear. They appear to have evolved to the state that they're
Yep.
at without any interaction.
Yeah. So we call that like dominated by secular evolution. So like slow internal processes. So, I mean, just intuitively, those are the ones you would expect to look for because basically if you have some like dwarf galaxy or something like that spins by and distorts the spiral structure, you're kind of pulling it away from whatever its equilibrium state is, right? So it's no longer connected to the overall dynamics of inside the galaxy, right? But to what degree, does that matter? I don't know. Like, could you just have a small perturbation and it's still okay? Like this previous galaxy here. Sorry, I'll go back here. Oops, one more. So like this galaxy here, right? So you have this short arm right there that doesn't really wrap around as tightly as the other ones. Like that could be due to an interaction or something, but to what degree does that matter? We don't know, right? I mean, obviously ones that are just shredded apart, right? That's probably not going to be useful. And so like another project that I want to do is, people have identified so-called isolated spiral galaxies, right? Where they're like distant, they measure the distance to other galaxies and they're separated by, great distances. So they probably haven't had an interaction with anything in, X amount of years, X amount of millions or billions of years, right? So they probably have just been left to evolve under their own, internal dynamics for a very long period of time. And so like one of the projects I want to do is basically pull out that like kind of subsample of galaxies and measure their pitch angles and then measure their black hole masses and see how well that actually corresponds. And if that's the better way to do it, is just you have to look for like really isolated galaxies to really get good correlations between black hole mass and pitch angle. I mean, that's not known either. Nobody's done that yet either. So, I mean, this is like, I mean, the thing is like, the stuff I work on, like nearby galaxies and spiral structure, is not the sexy thing, right? So there aren't a lot of people working on this stuff. It's like me and like some small groups elsewhere, and that's kind of it, right? Like everybody else is working on like really fringy stuff, like James Webb, looking at, these proto-galaxies on James Webb that are like 3 pixels, right? And it's like, oh, I can see structure in this. It's like, can you? Yeah, I mean, like I'm working on stuff that's nearby that's, much easier to see, right? And nobody really cares. Everybody's just trying to really push the envelope, right? Whereas I'm looking at like kind of the end stage evolution of galaxies. They're looking at the beginning stage of evolution. I'm looking at the end product and how we got to the end product, right? And so people aren't as interested in that. And so, yeah, I mean, if there were more people working on it, I think we have more answers. Like, how much do interactions really matter, right? So. Hmm.
So my what I noticed was look at both complex.
Hmm. Okay.
So there's 3 galaxies, and it looks like 2 of them are pulling M81 apart.
Right. Yeah. Yeah.
And it just
Right. Yeah. Yeah. Yeah.
it's just but Bose does not appear to be affected at all by that. It's just almost beautiful spiral galaxy.
I'm not that familiar. I'm not really that familiar with it, but is it? I mean, it just could be like it just happens to be in the field of view. Maybe it's at a different distance than the other 2. I don't know. Oh, they are. So they are same distance. So they are physically connected.
They're at the end of the vertices, but
Hmm.
So it's so but they I worked with another person at UNC.
Hmm.
She had developed a diagram for the gas interaction work, and they
Yeah.
had all that.
Oh, really? So they are interacting with each other. Hmm.
2 and M81 do not appear to be affected at all in terms of visually.
I don't know. I mean, it could also be. I mean, I don't know. I mean, it could be like 2 of them were already there, and the third one's like just came in now, and so it's like in the process, like it's just beginning. I don't know. I mean, again, I don't know. Yeah. I mean, velocity data would help, right? So yeah. Yeah.
So one final question before
Okay.
we break for our business meeting.
Okay.
Is there an email address or other contact info so that people interested could reach out to you with questions?
Yeah. Oh, you know what? I don't think I had my website on the beginning. If you go to my last name.github.io, so Treuthardt.github.io, that's my web page, and so there's like contact information there.
All right.
For sure, if that helps. So my last name, for people that are interested, is spelled Treuthardt.
And it's on the,
It should be on the
RAC
web. Yeah,
calendar. So.
or just look me up on the museum website. Yeah, I guess you could do
Yeah,
that too. Yeah.
Okay,
So, yeah.
awesome. Wonderful talk. Thank you.
Okay, thank you very
sir.
much.
Uh,
Yeah, thank you.